Hi there, Smart Drivers. Rick with Smart Drive Test talking to you today about road engineering and how road engineering has reduced the number of traffic fatalities, the number of traffic crashes, and made driving safer. However, this wasn't always the case. Stick around. Stick around. We'll be right back with that story. Hi there, Smart Drivers. Welcome back. A little problem with my tongue today, getting it to work and say words correctly. Carrie's here from Minneapolis, Minnesota, and she says it's in the high 40s and raining today. Ooh, that sounds yucky. High 40s. What is high 40s? It's like single digit in the Celsius, like 5 or 6 degrees Celsius. Oh, that is cold and gross and yuck. You want to dress warm for that kind of weather. So yeah, if you're tuning in or you're on the replay, let us know where you're tuning in from in the world. And, if you're working towards a license, if the test centers are beginning to open up, we are on day 26. We're almost up to a month here of lockdown. And during the lockdown, I'm going to be doing a live stream every day at 11 a.m. talking about different aspects of traffic safety and those types of things. This is all part of my story of becoming a driving instructor, going to university, working as a driving instructor, starting a YouTube channel, and helping people to be safer, smarter drivers. And Farron's here, so Farron can help me today with the road engineering aspect of traffic safety and whatnot. And Farron, I didn't ask you what kind of engineer you are, because there's many different kinds of engineers, and I was going to talk generally about engineering because and I realized I couldn't do that. I needed to talk about civil engineers who generally move into the specialty of doing road engineering. And then there are civil engineers who also just do traffic and how to set up traffic lights, how to, measure traffic density and those types of things, and then set up all of that information as well. So this is kind of a high overview of road engineering, and it's mostly related to road building. It's not really about automotive safety. Automotive safety is another whole other aspect of traffic safety, and we'll talk about that in the 1960s, which really is motivated by Ralph Nader's Unsafe at Any Speed, which begins to target the auto manufacturers and makes auto manufacturers responsible for making safer cars on our roadway. James, my friend, good morning. Finally made it a live one. I have to leave around 12:45. That's awesome. Thanks so much, James, for tuning in. Carrie says, so from yesterday, what is the number one reason why motorcyclists are killed in car crashes? Does the reason have anything to do with the dangers of left-hand turns? You are absolutely right, Carrie, and I completely forgot to answer that question that I posed to everybody about motorcycles. And yes, it is exactly that. That is the number one reason that motorcycle riders are killed in car crashes is other road users, mostly cars, turning left in front of motorcycle riders. That is the number one reason why motorcycle riders are killed. And there are some absolutely horrific motorcycle deaths, rider deaths on YouTube concerning motorcycle riders who have been traveling along roadway at a high rate of speed, and then somebody turns left in front of them and they die. Just absolutely horrible. Hussein, yes, the Chevy Corvair is exactly the car that Ralph Nader primarily takes aim at, and we're going to talk more about that. Lisa, my friend, how are you? So without further ado, let's talk a little bit about road engineering and get going on that. Again, as I said, if you're tuning in or you're watching on the replay, leave us a comment down there. Let us know where you're tuning in from, and if you have any topics you want us to cover, let us know. Janet's here from Ontario. Frederick is here from Denmark. Lisa and Hussein are here. Awesome. So we have a few people here. So one of the interesting things about roadways, and the first thing I'm going to talk about is trains. Trains came about at the beginning of the Industrial Revolution. They were a very early, technological advance. For those of you who don't really know what the Industrial Revolution was, it can be simply defined as a revolution, a mechanized revolution that changed because of two inventions. One was the steam engine, which allowed a power source, an indefinite power source. As long as you had fuel, whether that was coal or wood, to fuel a steam engine, you had power. Now, unlike horses that decided that they were not going to work after 5 o'clock in the afternoon, a steam engine, as long as you had fuel and you had firemen, which is interesting because today we think of firefighters as people who fight fires, but firemen in the 19th century and early 20th century were professions where people actually kept fires going in locomotives, in steam engines, in industry, and those types of things. So it was, the steam engine was one of them. The other one was the telegraph. Communications, your ability to communicate over large distances, and which completely revolutionized how we communicated with people, not unlike the computer communication revolution that we've experienced at the beginning of the 21st century. So the two technological advances at the beginning of the Industrial Revolution were the steam engine and the telegraph. There was fear around these technological advances. Some of you may have heard of the Luddites, and the Luddites, when the steam engine was attached to a loom and became a power loom, one person could now do the work of 300 workers. One person could do the work of 300 people. The Luddites came about because they began to go into factories and they would destroy power looms because they were afraid of advances and losing their jobs and losing work and those types of things. So that's where the term Luddite comes about. If you have somebody who doesn't have a cell phone, for example, and you call them a Luddite, that's where that originates from. Farron says, I'm an electric engineer, thus Lightning Farron. Heavy and light current now, and I will also study mechanical automotive engineering in the future, hopefully. Awesome. That is really great. So I don't know how much you can help me with civil engineering then. I don't think there's a lot of crossover. Anyway, so with trains, what happened with locomotives, we had these big steam locomotives at the beginning of the 1800s, in the 1830s and whatnot, and they tried to bring these on roadways for farming and those types of things, but the general public, there was so much fear around mechanized transport on roadways that they were relegated to railways. They had to be on tracks. So people could know where these mechanized machines were, because there's all kind. We're still talking of a time at the beginning of the 19th century where state and religion were very much one thing. I mean, we didn't begin to see the separation of church and state until the beginning of the 20th century, and people were like, "Oh my God, the devil! It's the devil incarnate, right?" So we had trains. By the end of the 1800s, you begin to see locomotives on roadways for purposes of farming and industry and those types of things. And some of you may or may not have heard of the red flag law. The red flag law was a real thing. And essentially, when these locomotives were being moved along roadways, there had to be minimum 3 people on the roadway escorting this machine, walking along beside it to warn other traffic. And the person in the front had to be walking carrying a red flag. And the reason that this got so much attention in the 19th century was that people believed that these were dangerous and that they would spook horses and that it would put other people at risk. And when the first motor cars began to make an appearance, the red flag law was applied to some of the cases. Not a lot of the cases, because it was very early on in the motor car, especially in England, when motor car legislation came about. And some historians like to say that there were cases that the red flag law was applied to. It wasn't true at all. It was other legislations. There was plenty of legislation and laws to police traffic on roadways. So there's public fear around mechanized transport. Thus, we had trains, because we could relegate trains to a very known space. There's railway tracks, and there's where the train is, right? But when they're on roadways, then we have public fear. And we had a lot of public fear around cars and roadways at the beginning of the 20th century. The reason for that is that roads were barely designed, especially in North America and in the west of the United States, in Canada, other places, Australia, and the world and whatnot. Many of these roads were little more than cow tracks through the bush or animal tracks through the woods. So, So what happened was you take the motor car and you inject it into an infrastructure that is not designed for high speeds of travel at all. And I talked about the other day that it was the Model T in the United States of America that very much broke down rural isolation, because the Model T had a very high center of high clearance. It was able to navigate rough roads, cow tracks, mud, snow, those kinds of things. So it really broke down rural isolation in the United States of America in the 1920s. Interesting enough, it was the Volkswagen Beetle in the 1950s and 1960s that broke down rural isolation in Australia. Again, because it was easy to fix. It could run on just about any kind of fuel. Some of you may or may not know that the Volkswagen Beetle had an air-cooled engine in it. It was not a radiator, liquid-cooled system as many of the cars are in this day and age. It was air-cooled. It was easy to fix. It had very little horsepower, but it was robust and could go. So the point is that a lot of the road engineering features that we enjoy in this day and age that we don't even think about in terms of many overpasses and bridges and types of things on roadways and whatnot. These things did not exist in the early part of the 20th century when cars came. I mean, the other thing, the first stop sign it's put out there that the first stop sign was created in Detroit, Michigan, when a police constable simply took a square sign and cut the corners off of it to come up with a stop sign. And I believe that was 1912 that the first stop sign was in. But there was no signage to direct traffic in cities because, as I said to you previously, most people lived in rural communities. They lived on farms. Most people did not travel farther than 20 miles from their hometown or their home their whole life. So signs were not needed in most communities, within towns and those types of things. And it was only with the motor car that we began to see signs appearing to direct traffic and to allow people to route plan and navigate. None of this existed in the days of horse and buggy. And, it's interesting if you go back and look at some of the archival material of the AAA, the Canadian Automobile Association and whatnot, and some of these early pioneers, some of these early motorists who were driving around in rural areas and those types of things, and having difficulty finding where towns and those types of things were because, there was no signage to indicate which town they were in and whatnot. And, there's all kinds of recorded stories of people driving automobiles across the United States of America or in Europe from place to place. This was a real pioneering exercise because, roads didn't exist. Roads were washed out due to flooding, those types of things. And this is all part of the road engineering exercise that road engineers were required to look after. How to deal with water, how to deal with wind, weather, rain, how to deal with snow and those types of things because the traffic had to get through. I mean, we have a huge infrastructure that, most of us wouldn't even give a second thought to keep roads open in the wintertime. I mean, the number of snowplows and winter maintenance crews are incredible, not to mention the construction crews that work on bridges, work on roadways, potholes in the spring, winter, the transition from winter to spring is incredibly hard on roadways, and roadways have to be built to sustain that. I don't know how much you know about road engineering in terms of dealing with frost. There has to be a base underneath the roadway. The reason that we get potholes in roads is because in the wintertime, the earth underneath the roadway freezes, and as you may or may not know, when you freeze water, the molecules in the water get closer together and ice shrinks, and that's why ice floats on top of water, because the molecules get closer together. So when you freeze the roadbed, the molecules of water get closer together. In the spring, when it thaws, what happens is the water thaws underneath the roadway. It expands, and expands the dirt and soil underneath as well. You get a soft spot in the roadway, and with the constant going over of vehicles and whatnot, you get a little indentation, And once you get a little indentation, then you've compromised the road surface. And now what's happening is the wheels of the vehicle are now pushing down on that every time they go over at high speeds. Boom, boom. And the deeper it gets, the deeper that the wheel goes into that indentation underneath the roadway. And it's a huge challenge that road engineers have not yet solved that provides a perfect solution yet. I mean, don't get me wrong. Road surfaces are way, way better than they used to be, but they still face that challenge in terms of road surfaces and whatnot. And a lot of the road engineering in terms of civil engineering dates back to the Roman era in terms of looking at how the Romans built roads to sustain horse traffic and whatnot. So there's a lot of thinking, a lot of very smart people who are involved in building roadways, culverts, bridges, those types of things. 380, how are you, my friend? Ice density backwards. Expands when frozen, contracts. Oh, did I have that backwards? Sorry. Thanks for clarifying that. Okay. Yes, I had that backwards. Exactly. 380, thanks for correcting me on that. Right. Ice expands, and then it contracts when it becomes water. So what happens is when it freezes in the wintertime, it pushes out, and then it contracts and leaves spaces in the soil in the spring. Yeah, I had that backwards. Thanks for helping me with that. Blue Rage, I saw Jurassic Park in thumbnail and was confused to see advice for driving. Glad I came to watch anyway. Yes, we're in the... And speaking, I'll clarify this here for you. Just bear with me, and I'll show you why I put that up there. Some of you may or may not. Farron, I know a few civil engineers. My friends and I are in electrical and mechanical engineering classes, made fun of our fellow civil engineers. Their classes were so easy, especially the math. Farron, but in all seriousness, I respect civil engineers very much. They are very good and hardworking in this difficult field. Some of my friends are civil engineers. Excellent. Always welcome. How are you, my friend? I'm awesome. 380. Okay, so I want to know, I'll just answer Blue Rage's question about Jurassic Park and why I said that. Some of you may or may not know about the Tacoma Bridge, and I'll just show you this. This was 1940. This is one of the things that fascinated me about civil engineering, and I probably would have become a civil engineer had I been able to do the math. But I can remember going on 2 or 3 field trips to the wind tunnel at Western University and learning about bridges and learning about buildings and the effect of wind on buildings and bridges and other structures, and learning about the Tacoma Narrows Bridge here. And and so here I'll just play this for you. Transition over. There we go. And full screen. There we go. All right.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's 3rd largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
So this is 1940 that this bridge collapses, and this is 3 years after the Golden Gate Bridge opens up, and this is one of the features that engineers, road engineers, bridge engineers, engineers that design and build bridges. This is one of the things that they have to contend with is wind. And what happened with the Tacoma Narrows Bridge is that it was incorrectly designed so that it would catch the wind. And what happened is that Blue Rage, no, this isn't fake. This is this is real. And so what happened with the bridge is that the wind caught the bridge, and think of it like a swing. So what happened is that when you get on a swing, you start out a little low and you push a little bit more and it gets higher and higher and higher. And that's exactly what happened with the Tacoma Narrows Bridge, was that the wind caught it, moved a little bit, and then it would swing back. The wind would catch it again, move it a little bit more and a little bit more and a little bit more. And with a constant wind, it set up this swing motion. And they actually, in civil engineering, they can actually show you that the frequency that was required for that bridge to actually collapse. And so the reason I put up the we're in the hands of engineers is because this is one of the trial and errors that happened with building bridges and making bridges better. And exactly what Cougar says here, the truth is suspension bridges are still the most effective if built right. Ice bombs on Newport Man Bridge wouldn't have happened on suspension vertical cables. And you're absolutely right, Cougar. Suspension bridges are indeed still viable in terms of building bridges. There's no doubt about that. However, they have to be built in such a way that they don't act as a sail, so that somehow the wind is deflected over the bridge surface, so that it deflects the wind. And it was fascinating. The other day I was talking to you about my kids, and we were watching that thing on skyscrapers and how they built skyscrapers taller and taller. And the Flatiron skyscraper in New York City, which is one of you've probably seen pictures of it. It's the Triangle building. It's shaped like a triangle, and it's in John Wick. It's featured in John Wick. What happened was after they built the building, it set up its own wind pattern at the bottom of the building, and men used to go there and hang out because women would cross the street and it would blow up their skirt, right? And this is what happens with many taller structures. I'm kind of off on a tangent now, but this is, and so the wind tunnel at Western, this was one of the things that they were doing with buildings, was figuring out how to make buildings taller so that they would sustain the wind. And essentially what they did was they designed the building structure in such a way that it would actually move the wind around the building or deflect the wind. It wouldn't actually catch the wind, it would actually deflect the wind. And the other issue with bridges and structures is it's not just the wind pushing against the building or the structure, it's the vortexes on the other side that are created. It's the same thing. Think of it like when you're driving down the highway and you're behind a semi truck. When the wind comes off the back of the truck, it doesn't just blow past the truck or the vehicle. It comes off the back and creates these vortexes. And that's the same thing with buildings and structures. And that's also a problem that engineers have to deal with when they're building these. So DC looks like a cartoon. No, it's just very, very old footage, probably 80 years old now. So that's why they have that whole, omniscient voiceover, which is always interesting. Cougar, the longest suspension bridge is in Japan. And the other thing that's interesting, Cougar, about the Tacoma Narrows Bridge was that was in 1940. The Golden Gate Bridge, which is a little bit more than a kilometer long, it's 1,200 meters, which is, I don't know, what's 1,200 meters, it's about 1,300 yards. That the Golden Gate Bridge has never had that same issue, even though it was opened and built 3 years earlier. So interesting comparison that one bridge was a suspension bridge the same as another bridge, but one bridge doesn't stand up to the wind, but the other one does. Carrie, thankful for the engineers who helped to make our roadway safe. Would not want to be driving on a bridge like that one. No, unfortunately, Carrie, that bridge was only open for a few months before it collapsed. Janet, last year I worked for a company working under civil engineers, then an electric engineer. Really enjoyed it. It was very interesting. And it is. Engineering is absolutely fascinating. Okay, who else we got here? Farron, an engineer's worst fear of projects breaking. If they break, our careers will plummet. This is my worst fear. People could die or be seriously injured. Yeah. Unfortunately, not all our on-paper calculations reflect in real-world situations. And Cougar, could you build an observation deck on a suspension bridge? Cougar, I suspect that you could. I don't see why you couldn't build an observation deck on a bridge. And that's probably something that we could pass over to other people. And so, kind of interesting in terms of bridges and construction of bridges and the challenges that engineers face. And Farron can probably speak to this, in terms of the challenges that electric engineers face and other engineers and those types of things. And it's as Farron says, you don't want this stuff to fail. And there, highways and interstates all over the world. The 401 highway in Ontario had a huge sinkhole open up that stopped traffic for 2 days, because the issue is that when these sinkholes open up, and essentially what had happened was with the sinkhole on the 401 was that there was a culvert running underneath the freeway, and the water was supposed to go through the pipe. But what had happened is there was so much flooding is that the water began to erode the soil around the outside of the pipe, and eventually, it went unnoticed, and the water came through, and eventually from a very lower down underneath the road bed began to erode away the road bed underneath. And then all of a sudden in the spring, when the ice contracted and opened up all those spaces between the dirt and the road bed, it just created this enormous sinkhole that stopped traffic for a couple of days. So these are other issues that road engineers are dealing with in terms of building roadways and road surfaces and those types of things. I mean, water is another huge challenge for road engineers in terms of building roads. Epic, speaking of engineers, some of them will try to rebuild an asphalt interstate highway onto a concrete pavement section due to its longevity. Examples of this is I-90 west of Syracuse. Yeah, and concrete, I know that concrete has a huge longevity, and it does have some flexibility in terms of it, but I've driven on concrete interstates. They're terrible. They're awful. 380, notice how the Golden Gate Bridge is on a wider, shallower bay. The narrows are narrow. If I had more of a funnel effect for the wind at Tacoma. Yeah, that's a possibility. 380, it's I don't know if there's ever been a comparison done between those two suspension bridges. Cougar, I suggested to an MLA that they build a 10-lane suspension bridge to replace the Massey Tunnel to avoid ice bombs and lower maintenance costs. And yeah, there's another point that Cougar makes about tunnels, is that tunnels underneath bridges are incredibly expensive to run. They're not cost effective at all. The Golden Gate Bridge is also ghastly in comparison to Tacoma, which is a mere 4 small lanes. Golden Gate is 8 lanes? Yeah, it's 8 lanes and a double deck. As opposed to diagonal cables then had the original design. Frederick, the island Funen, where I live, is connected to the rest of Denmark with 2 suspension bridges across Little Belt to Jutland and Great Belt to New Zealand. Yeah, and there are some, Frederick, there are some phenomenal bridges in the world. There's no doubt about it. And I mean, they built the Confederation Bridge here in Canada, which connects Prince Edward Island to the mainland, and they connected that. They built that a few years ago. It's not a suspension bridge, but it's another incredibly long bridge. And there has been talk here in Canada for decades about building a bridge to connect Vancouver Island to the mainland, because it's an hour and a 40 ferry ride, and people, drivers, pedestrians, road users just do not like ferries for whatever reason. It's a little bit like that line about airports and ferry terminals, the Great Leveler. I mean, everybody's the same. So anyway, that's road building, and then new tech, higher rates of speed. Road engineering has been designed over the 20th century to accommodate higher road speeds, and the way that we do that is curves that are cambered. It's called cambered when you bank the curve. We have that on roadways. You have to get rid of water off roadways as well, so you don't have standing water, because you'll have hydroplaning, so that the roads are cambered out to the edges so the water flows off. And then of course you have to have drainage under roadways, so that the water doesn't erode underneath the roadbed and whatnot. corners and curves and those types of things have to be designed in such a way that, you know, cars can go faster around corners, as well that you can get larger vehicles like trucks and trailers and those types of things. And my friend Wheelman, who drives in Europe, can talk to you about driving in urban areas with a large tractor trailer unit and trying to get it around into, you know, cities that were not designed around motor cars. The, you know, cities, particularly in Europe, if you ever go to Europe, these cities were very much designed around the horse and buggy. So it's difficult to get vehicles around. Epic. Speaking of suspension bridges, they can also handle trains. Samples of this is Manhattan Bridge, and if you are designing them, you need to consider weight of trains and other vehicles. Yes, and Epic, this is the other reason for the bridge law with tractor trailer units, that there has to be 40 feet between the kingpin and the center of the tandems on the back, and that's exactly what you're talking about how much weight per square foot of bridge can that bridge sustain, and that's all part of the civil engineer's job when the bridge is designed. How much weight can that bridge hold? It's the same thing with the Ambassador Bridge in Detroit, Michigan. That is the bridge between Windsor, Ontario, Canada, and Detroit, Michigan in the United States. That bridge is the border crossing, and I have had many a day sitting on that bridge, and the bridge from one end to the other end is full of trucks. Trucks lined up waiting to cross the border. So that bridge, again, has to be designed in such a way that that it holds up a lot of weight. You know, it's the same thing if you get congestion on the Golden Gate Bridge or the Manhattan Bridge or the Brooklyn Bridge, you know, the Mackinac Bridge in northern Michigan. Any one of these bridges has to be able to sustain a full deck load of vehicles on it that can vary from different kinds of weights. Frederick, yes, used to go with the ferry to New Zealand as a kid. Yes, and you know, same thing in Australia. You want to go to the Outer Hebrides in Scotland, you got to take a ferry, right? And you know, some people do not like ferries. The Isle of Lewis, which is the outermost, it's the westernmost island in the Outer Hebrides off Scotland. I met a woman when I was in Scotland who said to me, she said I don't take the ferry to Lewis. She was from Lewis. Her family lived in Lewis, on Lewis. And she said, I just do not take the ferry to Lewis. She said, that North Sea is just the roughest crossing in the world. And I met a couple the day after I went to Lewis on the ferry, and they were coming off the ferry. And they said when they came across on the ferry in the North Sea, they had every vehicle in the car deck chained down. And not only did they have it chained down, the couple that I met said to me that when they left, there was 18 inches of water. There was this much water in the car deck when they drove off the car deck. Just, I would not want to be on that ship. I would not want to be on that ship at all. Carrie, the bridge collapse sadly reminds me of the 35W bridge collapse here in Minnesota around 10 to 15 years ago. Oh, you had a bridge collapse in Minnesota. And Joseph, how are you, my friend? And yes, there's a ferry between the two islands. Frederick used to go on that. That's awesome. And Janet says she doesn't like ferries at all. I've been on a lot of ferries in my life. I went to the Outer Hebrides. I've been on the ferries in Newfoundland, the main ferry that runs between Sydney and Port aux Basques. I've been fortunate. I have not experienced rough seas yet at this point. James, it's not the life expectancy of a tunnel greater than that of a bridge. That question, James, I could not answer for you. I would need to ask a civil engineer that question about tunnels having a longer life expectancy than bridges. James, short-term cost definitely higher if calculated over a 200-year life expectancy. Would it not be lower, even with replacing ventilation over 30 years? I don't know. From what I know, I would need to do a bit more research to answer that question, but my understanding is that tunnels are more expensive than bridges, simply because of the maintenance costs of running the ventilation in tunnels and electricity and those types of things. Okay. Wheelman, too bad European roads can't handle a Kenworth W900. Wheelman, most roads in North America can't even handle a W900 or a 379 Peterbilt that have a 53-foot trailer behind them. That is not something I'd want to be wheeling around a big city like Philadelphia, New York, Boston, other cities like that. And definitely some of the places where you're going there in Portugal and Spain and Europe and other countries. You'll definitely need to come over here and have a little drive on one of these big rigs for me. All right, so we covered a lot of stuff here, and we kind of didn't get up to interstate systems and whatnot, but what I'll do is I'll talk about those tomorrow. And Hall phase, did they know about the wind swinging when they were designing the bridge that failed? Obviously, they did not take that into consideration, Hall phase, or it was just something that, happened, that got away from them. Because people, engineering and whatnot make mistake. Just one last story was when I was living in Melbourne, the Westgate Bridge, huge bridge. It's over the Yarra River and at the mouth into Port Phillip Bay. So it's where the ocean liners come in from Port Phillip Bay, and they go into the Yarra River, and they're unloaded and loaded in the industrial area there in West Melbourne. And it's the Westgate Bridge. It's probably 30 meters. I know it's more than 100 feet off the water. And part of that bridge collapsed when they were building it. And it was, and again, you have engineers who are designing and building the bridge, but at one and the same time, up until some years ago, and this is still true in some places in the world, that the structure that the government authority is going to build goes out to tender. And there was no checks and balances in place up until, a few decades ago. And all of this in terms of infrastructure, road infrastructure and whatnot has changed in the last 25 years. But what happened with the Westgate Bridge is that, it goes out to the lowest bidder. The lowest bidder gets the contract to build the bridge or whatnot. What happened with the Westgate Bridge, it collapsed and like 100 workers died. I don't know the exact number, but it was in the scores of workers died when part of the bridge collapsed during construction. So the other problem with bridges is that you can't just squarely lay the blame at the feet of engineers. It's also the builders and the construction companies, because, up until a couple of decades ago, when there wasn't the quality control that there is now, part of what was happening is that the tender was going out to the lowest bidder, and the lowest bidder was cutting costs. I mean, watch the documentary on the building of the Brooklyn Bridge. The engineer who designed the bridge knew that the people weaving the cable were going to try and cut costs in terms of providing quality cable. And the engineer was smart enough that planned that in part of the design of the bridge, knowing that the cable was not going to be up to the high standards that it needed to be. And essentially what they did was they put in quality control. They had people who were inspecting the cable when it was coming out of the factory. But what happened was that the wagon that was carrying the cables would go around the corner. They would unload it, offload it, put on the poor quality cable, and then send that out to the construction site. That's how they were getting past the quality control of the cable for the Brooklyn Bridge. It was very much designed. So this happens. It's not just the engineers who are culpable for the failure of some structures. It's also the construction companies and the builders, and the failure of quality control of the materials that are going into this. And so a lot of other factors. Like I said the other day, nothing is monocausal. There isn't one single cause for all of the things that happen when things go sideways. Farron, when there is so much to consider when engineering, even I have forgotten some of the more obvious things. One time I designed a CPU but forgot to include the cooling system. Also, money limits us. Exactly, and that's exactly what I was talking about. Going out to the tender, going out to the lowest bidder. The lowest bidder is going to figure out how to cut costs to be able to deliver on the project. Carrie, there is a memorial on the 35 West Bridge today. The 35 West Bridge is a big bridge that goes over the Mississippi River. Yes. Look at the Kansas City walkway collapse. So there's been other structures that have collapsed and those types of things. So engineering gone wrong. But at one and the same time, some of the things that engineers have done in the world are absolutely mind-boggling and have made our lives incredibly so much better. I mean, here in British Columbia, the Golden, there used to be just a treacherous piece of roadway on the Trans-Canada Highway that you had to come through the mountains there, and they've redesigned all that. It took a couple of years for them to redesign it. There's a huge bridge that they built there that just makes that section of roadway just so much better. And another section of roadway, the Coca Hollow Highway here in British Columbia, that replaced the old Fraser Highway through the Fraser Canyon, reduces travel time between the interior of British Columbia to Vancouver by an hour. So there are some road systems in the world that are so much better than what they used to be. So we'll leave it there today, and tomorrow I'll talk to you about the interstate system in the United States and how that got built under Eisenhower, talk about these expressways in and around the world and how they are maybe moving more traffic, maybe not moving more traffic. So all the best, have a great day, and remember, pick the best answer, not necessarily the right answer.